I'm a PhD transitioning to a postdoc working at the IVM FU, mainly with the DIMCOMO. And I would like to speak to you about three main things. So compound events, extreme crop impacts, and storyline for attributing impacts and potentially look into transitioning somewhere into the future and think of potential adaptation planning related to crop impacts. Right. So maybe start by giving this disclaimer. Climate impacts on agriculture are systemic. So that's really a complex chain of drivers affecting each other, eventually leading to impact. So typically we have this risk framework that combines exposure, vulnerability and hazard, and then in driving risk. And within this, you have all sorts of feedback, influencing each other and eventually affecting this variable that we're interested in, risk impacts. And maybe to motivate this with a simple example, which is still a simplification of the actual risk framework, but this is the 2010 event, so that's, I think, quite known by many people. This is the Russian heat wave in 2010 that drove, well, maybe I have a laser. So this is the Russian heat wave in 2010 that affected the cereal yields, led to export bans. And at the same time, you had this excessive rainfall event in Pakistan, again, leading to shortage in cereal. And then all kinds of socioeconomic conditions starts to kick in. So you have panic buying, export bans, etc., affecting food affordability. And then depending on your vulnerability or where you are in the world, that can also lead to more impactful social events such as food riots, etc. Right. So given that disclaimer, I also want to highlight that here I will focus on the smaller portion of that big impact chain. And this is typically the climate linking to hazard and then the impacts. So this is a simplification, of course, and then it helps because you can narrow down the problem, but of course comes with assumptions. So then you would need to take that when you consider the conclusions of this work. But so this is a bit the setup, and I will use this compound event framework that has only recently been proposed, maybe the last 6-7 years, working with this compound framework. And I use a bit the typology that has been summarized in this review paper by Zeichler et al., basically narrowing down compound events into 4 types: preconditioned compounding, temporally compounding, multivariate compounding, and spatially compounding. And I will be focusing on the multivariate and spatially compounding in the context of crop impacts. So further narrowing down on the work that I will present, I will focus on the soybean crop, and I'll say something about this crop. It's a very particular crop where 70% of the global supply is produced in only 3 regions. I think this is maybe the only. Right. So this is the only crop with such a small community of producers around the world. And then you can see here in the bottom left, production across time, stratified into Brazil, US, Argentina, and rest of the world. And the main message is that these 3 countries dominate global production across time. So why so more on soybean? Soybean is the largest traded commodity and the second largest in terms of kilocalories embodied, and that is a lot related to the meat industry. So yeah, we focus on soybean, of course, all kinds of feedbacks. So diet related to climate change, but so that's my crop, maybe put it like that. And then I will cut my regions of focus into 3. That's the Eastern US, Central Brazilian region, and CESA. So CESA is grouping part of Argentina and parts of, well, the southern part of Brazil, which tend to have a similar climatology compared to the northern part of South America. So moving forward into these co-occurring hot and dry events and how they impact crop yields. So two things about this type of hazard. So hot and dry weather often co-occur due to circulation anomalies. So when you have a high pressure system, typically this favors hot and dry conditions. And then you also have the land atmosphere component, which when you have drier soils, you have less evaporative cooling, which tends to also favor higher temperature. So in one sense, we have dependence in the drivers themselves. And then when it comes to the impact aspect of things, we also have a dependence with respect to impact. So this is a simple mechanism by which to illustrate that dependence. There are many more other complex pathways for this dependence, but the simple example is that typically during drier soil conditions, the crop has less. Maybe start with that simple analogy. Crop is like a human being. It transpires, it sweats, but when it has less moisture availability, it tends to close its stomatas to maintain moisture in the crop. And when this happens, that means that it can transpire less, and then it becomes more sensitive to temperature. So that means that for a same level of temperature, dry conditions will make the crops more sensitive to heat. Right, so we estimate that going to data, and here we build a simple model that estimates yield, function of soil moisture and temperature. So what you are seeing here in the grids is yield anomalies and observed yield anomalies, and the contour lines represent model estimated yield anomalies, function of temperature and soil moisture. This is in Central Brazil, CESA, and the US, so the three regions I introduced earlier. And the main message here is that impacts both in observations and in model estimates tend to really focus in that hot and dry corner of the space. This is another example to illustrate that. So if you take a column of fixed temperature anomaly, then you see that also both in observed and in model estimates for different levels of soil moisture, the yield estimate varies even for a fixed level of temperature. So this effect is also largely consistent across space. So that is the only message that I want to give here. So temperature is driving lower yields across both North and South America. Soil moisture availability increases our yield estimates, and then this interaction term means that there is this amplifying effect on yields from the combination of temperature and soil moisture. Right, so moving forward to spatially synchronized hot and dry events. So I'm focused on North and South America, and this is both these regions are well known to be impacted by ENSO. So what I show in the top is the canonical influence of ENSO via Rossby wave propagation in South America and in North America. Maybe one more thing about this typical ENSO evolution. So here we have most of the El Nino years, so the positive anomaly of ENSO centered here around the ENSO 0. And then the main message here is that the evolution of El Nino years tend to persist for more or less 1 year and then dampen off in the following year, whereas when we have La Nina years, these years tend to persist. And then you often have multiple year La Nina, similar to the one that that was just occurring a year ago, persisted over 3 years, I think. And Right. And there's a lot of debate of what is the forcing or climate change signal in influencing ENSO. And yeah, that's still, I think, unknown or largely debated, but I'll come back to that later on. So maybe a bit more detail on how this can impact crops in South America. So the dominant pattern of climate variability in South America relates to this seesaw pattern between central and Southeast South America region. So that's also one motivation why I divided these regions into two. So typically you would have the active or non-active phase of the South Atlantic convergence zone. When it's active, you have moisture transported from the trade winds into the eastern part via the low-level jet. Whereas when you have a high pressure system over here, this tends to push the moisture transport via this southern pass, taking moisture from the trade winds via the Amazon into the CESA region. So this is the dominant pattern of moisture variability, summer moisture variability in this region. And then the ENSO, of course, has this typical Rossby wave propagation associated with it that leads to the formation of this low and high pressure system close to the South Atlantic region that you see over here. So this tends to favor the activation or not activation of the South Atlantic convergence zone, which in turn influences the moisture transport availability. So whether we have low moisture in the central Brazilian region and high pressure in CESA region, or the opposite. And the counterpart, so the North American part, we also have this extratropical propagation of the ENSO anomaly via this Rossby wave into the northern hemisphere and the US region. So my colleague at the IVM, Sam Pfeifferberg, has done a lot of work on this, showing that associated to this ENSO anomaly is an extratropical sea surface temperature anomaly that looks like this, so a dipole in the northern part of the Pacific, which tends to favor the occurrence of this this wave train in the US, in turn influencing temperature and soil moisture anomalies in the US. So this is a bit the story that I've collected within the literature linking ENSO to these two regions. And now I summarize this. So this is the South Atlantic pattern that we've discussed earlier. This is ENSO, and this is the North Pacific pattern for the US. So if we put all of this together in one causal framework, so that is that translates into ENSO in Austral spring, linking to spring soil moisture both in north in CESA region and central Brazilian region, and then moving on into summer, affects the South Atlantic pattern, which is summarized here, and then affects soil moisture both in CESA and the central Brazilian region, in turn affecting yield. And then here you see this anti-correlated effect onto the CESA and central Brazilian region linked to the South Atlantic pattern that we discussed earlier. Right, so the main message here is that we test out these causal assumptions that we make, and we indeed see that the signal onto summer yield anomaly in South America is mostly conveyed by the South Atlantic pattern, so no longer really linked to ENSO, but to the ENSO signal conveyed fully by the South Atlantic pattern. And a similar story emerge for North America, where most of the signal in summer is contained in the North Pacific pattern, which is influenced, of course, by spring earlier in the season. To further summarize, I didn't discuss really the impacts of ENSO phases, but this serves as a good summary. So we conclude that persistent La Nina years can drive synchronized failure in US and CESA region with such imprint. So typically in these persistent La Nina years, you would have drying in both the US and CESA. and in central Brazil, the opposite of XAIDA region. And then you would also have extreme heat in the US and XAIDA, which often translate into crop yield anomalies in these regions. And then I want to pinpoint one specific event out of this persistent La Nina events, and that is 2012. So 2012, in terms of sea surface temperature imprint, had this persistent La Nina signal going from October, November, December into boreal summer, and indeed reflects these South Atlantic pattern that we discussed earlier and the North Pacific pattern that we discussed earlier. And that imprint we can also see in the yield anomaly, summer temperature anomaly, and moisture anomaly. So that 2012 event just follows exactly from the dynamics I've just discussed earlier. So why this event? Because if you look in the global production time series anomaly, that stands out as the unprecedented production shock. So what happens when we have these simultaneous shock, typically, especially for soybean, because of this small community, that leads to consumption, global consumption larger than global supply. And when this happens, often you have this mapping out onto price, and therefore risking this cascading impacts into the food impact chain. Right. So then one wonders what would be the impacts of such event in a warmer climate. So such question is not simple to answer because I've highlighted a few uncertainty question marks that I highlight. For instance, we are still not really sure on how ENSO will respond to global warming. So whether we will have more La Nina, El Nino type of years, whether we will have more persisting El Nino or La Nina events. Then there's also a lot of uncertainties related to land atmosphere feedbacks. There's uncertainties related to the frequency of hot and dry events linked to uncertainty in precipitation trends. Then we are not sure of the warming level, management conditions, and what policies will occur influencing such impact chain. And one specific element of this uncertainty I want to highlight is the ENSO component. So I thought this graph from Seeger et al. Is quite striking. In red is El Nino-like trends, and in blue is La Nina-like trends. And I want to focus on this right-hand part of this graph. So this is multimodal large ensemble estimates. And then you see that in this quadrant, model estimated trends, and in this quadrant in blue, the observed estimated trends. So this is an ensemble of observation. And what is very striking is that most of these large ensemble model estimate tend to predict actually trend towards El Nino conditions over the historic periods, whereas what we observed is a trend towards La Nina period. Simple message is that then doing projections based on such or inferring future impacts based on such projections should raise some question mark. And that is the motivation for what we use here for estimating these future impacts and attributing observed impacts using the storyline framework. So this is from Shepard 2019, and Ted maps out this very nice graph that shows a bit the key components that can influence climate impacts going from climate forcing into global warming, etc. So what we do here is that we do a conditional attribution study, and that means fixing a few nodes in that system and allowing others to change. And yeah, so I think the main motivation, for instance, here for fixing the dynamic conditions is we are not so sure of the future frequency of El Nino versus La Nina, so might as well just take that for a given and estimate what would be the impacts of a specific event, 2012, for instance, under future warming conditions. So just to summarize, And of course, I mean, I did mention that initially that we have a very complex risk framework, but here we are fixing exposure and vulnerability. So in a sense, what we're assessing is the thermodynamic effect of global warming onto the regional warming hazard and climate impacts. This is similar, but maybe a bit more graphic. So we take that event, the 2012 event, we fix the circulation observed during that event, the large scale circulation, and with a knob, just change the global warming level towards a pre-industrial and a +2°C degree warming. And yeah, one more slide to motivate the method here. So these are nudged experiments. 3, counterfactual, a world without climate; factual, the world as we know it; and a +2°C simulations. These are taken from the work of Linda van Garden, which documents that in already 2 published papers. This is based on the ECAM6 model. So 3 different storylines, 3 members, each for the 5-year period, and we're mostly focused in 2012 within that time bracket. Right, I hope that is, I mean, we can come in the discussion a bit more if necessary about the details of this method. But the main message is that we fix the large-scale circulation and then allow thermodynamic response of temperature and soil moisture close to the surface. And then we see that, pre-industrial temperature is cooler than the factual. That is more or less expected. And then we see that the +2°C world is warmer across the board, so both in North and South America. Soil moisture changes do not vary that much, so we see more or less the same drought level across storylines. In terms of yield impacts, we see this amplifying yield impacts at the county level, going from pre-industrial to factual to +2°C. Finally, summarizing this, we came to the striking conclusion that if you compare pre-industrial 2012 aggregated anomalies versus factual, we note that half of this unprecedented global soybean production in 2012 is attributable to climate change, thermodynamic component of climate change. And then if you want to dig a bit more in detail in how these effects are happening, we see that on the top left-hand side of the graph, this is yield anomaly function of summer soil moisture. And here in the vertical line, we see the different storylines. So although we see for the 3 regions that soil moisture doesn't vary much, increasing temperature means increased sensitivity to soil moisture, and therefore higher impacts from soil moisture in a warmer climate, even for similar level of drought. And with respect to temperature, it's a bit more simple. So it's just an increase in the absolute level of temperature driving higher yield anomalies. So thank you for your attention. And that is the message I wanted to deliver today.
Thank you very much for your presentation. So now if anyone has questions, please raise your hand or use the chat, however feels more comfortable for you.
May I, Maria? Oh, if there's somebody in the chat, I think. No, from Sonia.
Yes, Sonia says a small comment on the simulation setup.
Yes, I agree. I think Sonia mentions that it's a similar setup to the one used in previous studies from your group. Yes, it's true. I was also aware of this. But I think the collaboration with Linda was mostly around that 2012 event, which she also did a few studies on.
Yeah, it's actually correct. Yeah, Sonia, it's very much the same type of nudged atmospheric simulations. We never did the extreme X simulations in different climates with Easy Earth. So that's why this type of storyline approach. Did you do that actually with SESM, Sonia?
Yeah, we actually did it. So we have another paper, not the one but we had another one which we call storylines with Catherine. So I'm going to include it in the chat. So with one where we set storylines of the 2020 summer, was it 2018 summer? But anyway, so where we did exactly the same setup, where we basically used the circulation anomalies and modified the climate. I'm going to include this link as well.
Yeah, Pascal, go first, please.
Yes, thank you, Raed, for this very nice presentation. So I have a very naive question, because here you focus on soybean, which is produced by only 3 countries. So would be the conclusion of your story that we should refrain from growing, we as human beings should refrain from buying or having a soybean, on having a more diverse sources of food for us, or the cows or whatever, so that just because what you suggest is that there is a risk of a collapse of the production of soybean with climate change. So is there a danger of a global starvation due to the destruction of crops? So that's a very naive and very general question. I apologize for this.
No, I don't think it's a naive question per se. So I also struggle to convey that message, but you can also think that the soybean is mostly produced indeed for the meat industry, and then the meat industry is a big driver of climate change. So I avoided going into these larger feedback loops. So there is a lot to consider of with respect to what we should do and what we should not do. But maybe ignoring that more complex framework and focusing on your question. So indeed, soybean is this very particular case where production is only in these 3 regions, and that makes it extremely sensitive indeed to these simultaneous breadbasket failures compared to other crops. But how people deal with this, I know that in Europe, there has been a lot of recent studies investigating growing soybean in Europe. So that could be one way to mitigate that issue, diversify production areas of soybean if you want to further continue consuming that crop. But indeed, it raises the alarm that simultaneous breadbasket failure are particularly an important impact for the soybean crop, for specifically the condition you mentioned.
Okay, so just a follow-up question: is there a risk of a global failure of the soybean production for a given year or a given set of years with the climate change? Have you looked at this?
So given our understanding that these global failures are very much influenced by ENSO and La Nina events, and I started with this motivation from the Seeger paper that these future projections in frequencies of El Nino, La Nina are highly uncertain, and therefore very difficult to estimate that via the projections. So what we use here is this storyline approach and simulate that very impactful event in a warmer climate and see that the impacts are indeed larger. So in that sense, given our conditional assessment of future impacts, they are indeed larger on soybeans. So if that event were to occur in a warmer climate, impacts will be larger. And we don't assess cascading impacts. There are a lot of non-linearities there, so I'm not sure whether it will lead to starvation or just people losing money. That is a question we don't really go into, but impacts with respect to crop yield anomalies are larger.
Thank you.
Sure.
Yeah, just to, I mean, but Raed, I guess the very strong concentration into these 3 regions, that is really the risk amplifier, right?
Yeah.
And
So
that is, I mean, it's kind of extreme for soy, but you have it for more type of crops, that you have that increasing concentration of where production is taking place. So that might be it might be advisable to not have that high level of concentration in general.
Yeah, so there is one thing towards, but usually what happens is that countries that are big producers have a comparative advantage in making money out of this crop compared to other regions that would start to build this and not make money. Like wheat is a big example. For instance,
you mean like it's an economic efficiency increases, and then
like just saying that diversifying is not so straightforward because, for instance, the Middle East is highly dependent on wheat, but doesn't grow wheat because it's a net loss if they. So it is cheaper to import wheat than grow wheat themselves. So there are a lot of consideration to take in once you assess this. But also here, I highlight this persistent La Nina and its impact on soybean, but other configuration of ENSO can lead to compensation between the 2 regions. So often failures are compensating across regions. You just have these specific cases where the impacts are amplified. So these 2 components can occur.
Yeah, so I had 2 other questions actually, Raed. And by the way, very nice talk. You really covered a lot of work. It's very nice. So yeah, a small question that which is to do with the non-linearity in the crop impacts that you see for the US. We discussed this a while ago. Did you ever figure out why that is? If you go from pre-industrial to present day and then to 2 degrees? Still curious.
You are referring that we see in the storylines that the warming from pre-industrial to factual is much smaller than from factual to +2 in the US.
Yeah, I think it's basically in your previous slide or one before, like
yes.
Yeah, here, like if you look at the US, so this is the most right bar.
Here. Yeah, I think so. I mean, discussing this with Ted, his idea was that you would still, because of the sea surface temperature warming pattern, you would still see influence on these where these high pressure system occur, even though you are nudging the large scale atmospheric circulation closer to surface, you would still have some kind of variability. So that can lead to such influences. Yeah, I was thinking that it could be the soil moisture component with these land atmosphere feedbacks kicking in, but here we see not much change in the drought, so that's possibly not the case. But yeah, so
okay, so the crop impact, the high crop impact under 2 degrees C is really due to the strong temperature.
It is mostly related to temperature, but the effects of drought are not independent of temperature. So, yeah.
But okay, yeah. My second question was like, I think you in your introduction to your presentation, you aimed already a little bit at it, that these storylines. This is really a climate storyline, but in principle you could enrich that with more like adaptation approaches, right? Have you thought a bit more about how, for this particular storyline study, how one can do that? What type of things one could add?
So there are some radical things that people can do. For instance, if you consume less meat, then maybe that is great for the whole impact chain. So probably you're mitigating some of the greenhouse gas emission. you're reducing dependency on
Yeah,
soybean.
yeah, okay. But I mean maybe more like specifically for this like 2012 study where the warming is leading to much stronger impacts. So what type of adaptation is then possible to avoid such crop risks, crop losses? And can one include that in a storyline study to show this quantitatively?
Yeah, so you can irrigation. Of course, that is a common one, but you would also think that climate change will impact your availability of water for irrigation.
Right.
But often irrigation has been shown to really almost decouple weather from crops. So crops can sustain actually 40-degree sea temperature in the wild, at least based on these large scale estimates, given a good level of water in the soil. That could be one way. If people would store a bit more, so this shortage is often linked to people storing and not storing enough. So if you would know, maybe if you have a good early warning system and you would know that this would occur at some point the next year, maybe you would just increase production in the previous year and store a larger amount of supply.
Okay, thanks a lot.
Sure.
There are a couple of questions in the chat.
Yes, so there's a question on the conditional independence tests. And all the well, we assume here linear functional relationships, and the conditional independence test is as simple as a multiple. Well, we take the basis set from the causal hypothesis that we have, and then we just build the various regression equations that would imply the conditional independence test. So if A causes B causes C, then A and C should be independent given B, and this is basically the coefficient attributed to B in the regression model.
So that boils down to using partial correlation analysis, right?
Exactly. Yes.
Okay. So that's, I don't know how strong is the assumption of linearity and causality then.
That is a good point. Yeah, I think these are important questions once you want to push the robustness of the estimates we find here.
Yep. Thanks.
And then there's another question on the chat. Like a small clarification. Yep.
Did you use the KNMI lentis simulations as the reference is missing? Yeah, I didn't use them. Okay, yes. Well, if they are useful, then maybe nice to reach out. Tell me how they are useful. Yes, maybe another question.
Yes, Pascal.
Yes, the last comment, which is, do you intend or have you applied to the XAIDA summer school at the end of May? Because I suspect that you would have a lot of things to say or during that school.
Yes.
So also an advertisement to the rest of the audience, to the school, because the deadline for application is tomorrow. So if you haven't done it, then please send your application. But Raed, I hope that you will go.
Yes, I will be. Well, I did apply.
Great.
Yes.
Okay, you can find the link for the summer school on the chat for those of you who are interested. And if there are no more questions, maybe we can wrap up the session. So if anyone else has some doubts or so, last minute. Okay, so thank you very much for everyone that attended, and we hope to see you on the next session next week. Next month, sorry.
Yes, thanks, Raed. Thanks, Maria.
Thank you. Bye-bye.
Yeah.